we have studied about resolving power. There are two particles here. These are the sources of light, and I want to see them separate. This is opening of an instrument. This instrument may be our eye. This may be microscope, telescope. And here is a screen. This screen may be screen of the microscope, telescope, or retina of our eyes. Then this makes a maxima here. This makes a maxima here, and we are able to see the difference if there is a darkness here. Then we are able to see this distance. Now, the minimum angle at this point, delta theta. This is a specific angle for each and every instrument, which tells us whether we can see them separately or not. For my eye, this delta theta is about 1 minute. If there is an angle less than 1 minute, the things are so close that this angle is less than 1 minute, then I will not be able to see them separate, and in that case the two maximas maybe they will interfere like this. So I will be able to see one full spot, that will be 1 and not 2. So this is minimum angle for resolution. Minimum angle for resolution, delta theta, when I see them separate. This is the distance d, minimum distance of resolution. And this will be wider depending at what distance is this screen. Okay, this is what we have understood. This is what we have studied. How we can apply it in microscope. Another thing, yes, this is minimum distance. What do we term as resolving power? Resolving power. Less is the distance, more is my power. जितने छोटे डिस्टेंस को हम देख सकेंगे अलग अलग, तो हम बोलेंगे हमारी पावर ज़्यादा है. So resolving power P is 1 upon D. This is resolving power of an instrument, inverse of the minimum distance. Okay, with all these things, we would like to see microscope. In case of microscope, here I place the object to be seen. This is opening. In the opening we have fitted a lens which we call objective lens, and this is the screen where we form the image, wherever the image is formed. Okay, so we also know a formula for this, that how much this distance should be. For clear resolution, delta theta should be is equal to 1.22 lambda upon A, where lambda is wavelength of the light, and A is aperture of opening. Here it is aperture of this lens. This is A. Lambda, whatever is the light. So these are few things which we have already studied. How to apply it in microscope. See, this is objective of a microscope. It has got a focal length f0, and we are required we want to keep our object very close to focal length. तो हम अपना ऑब्जेक्ट यहीं कहीं रखते हैं, जस्ट आउटसाइड द फोकल लेंथ. तो हमने यहाँ पर अपना ऑब्जेक्ट रखा. यहाँ से ये जो ऑब्जेक्ट की लोकेशन है, इस लोकेशन से ये जो अपर्चर है, दिस डिस्टेंस और दिस डिस्टेंस, इफ वी जॉइन दीज टू, देन लार्जर इज द अपर्चर, लार्जर विल बी दिस एंगल. तो ये एंगल हमको अपर्चर के बारे में बताता है. देयरफॉर वी गिव इट ए नेम बीटा. ओके, इफ दिस इज रेडियस, this is A, this is A, this is equal to A plus A. This is A, this is beta, and this is the distance between these two. So we know A upon beta, A upon this, let us say O. M. N. A mn upon om, mn upon om, or om is equal to sine beta, or we can say mn which is equal to A is equal to OM sine beta. Now this OM or this ON, they are very similar to each other, they are very close to each other. So, and this length is almost focal length. So I can write it A approximately equal to FO sine beta. So this total 2A, if necessary I can write it 2A is equal to 2FO sine beta. This is a relation between this aperture, focal length. Focal length is property of the lens, aperture is again property of the lens, and this is kept at a distance FO. So this becomes the relation. So this is also known as optical aperture. Now here we have two objects which we want to see them separately. We want to see that they should appear separate, and there is a distance between them, and that distance is small d. Now I make a diagram here separate. Here is the opening which I will show like this. This is a opening, this is covered by lens, and I will make that old diagram again. Here we have these 2 points which we want to see separate with a distance small d with them. Now if this is the minimum distance which can be resolved, इससे कम डिस्टेंस होगा तो हमको नहीं दिखेगा, तो इसको क्या बोलते हैं, मिनिमम डिस्टेंस ऑफ रिजोल्यूशन. ओके, यहाँ तक अभी हमको सेपरेट दिख रहा है, तो इसका मैक्सिमा यहाँ बनता है, इसका मैक्सिमा यहाँ बनता है, एंड वी आर एबल टू सी देम सेपरेटली. Okay, this angle we have already given the name delta theta. Now this is a lens. If this distance is u of the objective, this distance will be v for the objective. Now we have certain relations. These are the 2 points, and these are the 2 points of the image. If this distance is small d, then let's give certain name to this distance. and let this distance be capital D. Okay, this distance is D, this distance is U, this distance is small d, this is capital D, this is the opening lens. Now here we have certain relations. What is magnification? Magnification is size of the image divided by size of the object, and we can derive it that this is also equal to V objective upon U objective. Okay, here we know that object is placed very close to the focal length. Object focal length के बहुत पास है, इसलिए U approximately ये जो है U, this is approximately equal to focal length. So this we can also write as D by D is equal to V upon focal length, or D is equal to small d is equal to capital D, okay, into FO upon V object. Now, what is this minimum angle of resolution in this diagram? Delta theta is equal to, we have two relations for delta theta. One, our theory says, according to theory, if delta theta is minimum angle of resolution, then delta theta should be equal to 1.22 wavelength of this light divided by aperture. This aperture. Okay. This geometry says, according to geometry, here delta theta is equal to, this distance is D and this distance is V naught. So I can write it arc upon radius, D upon V naught. This is delta theta, and you see it appear here. So I write it again, this one. The distance, this distance, minimum distance for resolution. If this is the minimum, इससे और छोटा होगा, अलग अलग नहीं दिखेगा, तब डेल्टा थीटा की ये वैल्यू होती है. तो मैं उतना ही डिस्टेंस ले रहा हूँ. दैट डिस्टेंस इज इक्वल टू डी अपॉन वी नॉट, एंड डी अपॉन वी नॉट इज डेल्टा थीटा. आई राइट इट डेल्टा थीटा इंटू एफ ओ. नाउ हाउ मच इज डेल्टा थीटा इज इक्वल टू? Delta theta is equal to 1.22 lambda upon A. So this is 1.22 lambda upon aperture A. This is distance D, FO. Now this aperture, I have already taken one equation here which says this. This aperture, this total aperture is equal to 2f naught sine beta. Here don't get confused with A and 2A. Here I have taken it as 2A. Here I have taken it as A. So A in this diagram is equal to 2A. So here the total aperture, this aperture is equal to 2f naught sine beta. Here what is this A? This A, I have taken this. I should have taken it 2A. I cannot, but you can see this, you understand this, कि ये कितना है, aperture है, और aperture की value कितनी है, 2f naught sine beta. So this I can write as 2f naught sine beta. So this will be 1.22 lambda FO upon aperture. Aperture is 2f naught sine beta. Here f naught is cancelled and we get it 1.22 lambda upon 2 sine beta. Okay, this is, yes, so this becomes the smallest distance for resolution. Now this smallest distance of resolution, this much, I want to make it still smaller. अगर मैं और छोटा रिजोल्यूशन देखना चाहता हूँ तो मुझे क्या करना चाहिए? आंसर है ऐसी लाइट डालनी चाहिए जिसका लैम्डा और छोटा। तो छोटे लैम्डा वाली लाइट हम कहाँ से ला सकते हैं? हमारे लैब में विंडो से जो लाइट आती है, दैट इज़ ए नेचुरल लाइट, इट हैज़ गॉट ए पर्टिकुलर लैम्डा. ओके, I can put more light on the object, but how I can reduce lambda? So answer is, to reduce lambda we must pass the light through certain liquid which has got refractive index. Now the relation is, when a light pass through a liquid, then lambda through liquid is equal to lambda in the free space or air divided by refractive index. आप सबको मालूम है, when the light pass through a material, its velocity decrease. अगर velocity decrease हो जाएगी और frequency same है, then what has happened to lambda? Lambda has decreased. That is why velocity decrease. Air में अगर ये वाली wave है तो इसको जब हम पानी में ले जाएंगे तो इसका ये जो लैम्डा है this will decrease and the wave will be like this. So speed will decrease because lambda has decreased. This has become less. So this happens in liquid, this is in air. But this is very beneficial for us, क्योंकि अगर लैम्डा छोटा हो जाएगा तो हम और छोटे छोटे डिस्टेंस को भी क्लियर देख सकते हैं. तो हम लैम्डा छोटा करना चाहते हैं और उसके लिए हम लाइट को एक लिक्विड से ले जाना चाहते हैं. सो इन दिस माइक्रोस्कोप वी मेक ए कंपार्टमेंट हियर लाइक दिस, और इस कंपार्टमेंट में हम लिक्विड भर देते हैं. Now the light which is going to the opening from here, that light has to pass through the liquid, और इसका लैम्डा डिक्रीज हो गया. कितना हो गया? लैम्डा बाई म्यू. So now with the liquid I have to change this with lambda upon mu. So I will write it this way, with filling liquid between object and lens, small d is equal to 1.22 lambda upon mu. अब lambda की जगह कौन आ गया? lambda upon mu, where mu is refractive index. बाकी वैसा ही रहेगा, 2 sin beta. So this is the minimum distance we can observe through a microscope. Then what is resolving power of the microscope? Power is inverse of the minimum distance. 2 mu sin beta upon 1.22 lambda. Okay, so this is power. What power? Resolving power. Now you see, this resolving power will be more if beta is larger and mu is larger. How beta will be larger? This beta will be larger if this aperture is larger or this is closer. So ये aperture तो हम बहुत बड़ा नहीं कर सकते, पर अगर फोकल लेंथ छोटी लेंगे तो फोकल लेंथ यहाँ तक ले लिए, बीटा बड़ा हो जाएगा. That is why the focal length of microscope should be small. ये. So this is power, और इससे हमको क्या दो रिजल्ट मिले? Focal length of objective should be small for better resolution. What is this? Mu. The liquid should have a high refractive index. Then this will be n. The light used should have lower wavelength. So this is the resolving power of a microscope, and next we will see resolving power of a telescope. Resolving power of a telescope is not having much of derivation. We know delta theta, minimum angle to be resolved, is equal to lambda upon aperture. The same formula we are using for telescope. You see, telescope has got a lens which is objective lens, and this whole objective lens acts as opening. The light is coming from the space, and that's a very large space. From that, all these lights are coming. How much light we are gathering? We are gathering only this much light. So, if this aperture is large, then the angle should be small, and if angle of resolution is small, that means we are resolving it better. So, for delta theta to be smaller, A should be large. So what is resolving power? Resolving power of telescope is equal to A upon 1.22 lambda. This is resolving power of telescope. Very simple. So aperture should be as large as possible. That is why it's a very famous question, why objective lens of a telescope is kept very large. Answer: larger is the aperture, more is the resolving power, and we can see all the spots of the star separated. Otherwise, we will see a smudge, that is all overlapping, mixed up together. If we want to see them separate, then aperture should be large as possible. So, what is the property of telescope? The property of telescope is not magnifying. The property of telescope is resolving. When we resolve and make a very small diagram of the star in which each and every particle looks separate, and then magnification is no problem. We simply keep an eyepiece and see them magnified. But unless they are resolved, the magnification will not help. That you have seen in the previous lecture. So this is resolving power of telescope. So we have seen resolving power of microscope, resolving power of telescope. While microscope, our thrust is to magnify the small thing. What is our thrust? To magnify. In telescope, our thrust is for resolving. Because far off things, we want to resolve more and more so that we can see them separately. So this is resolving power of microscope and telescope.